Hi, and welcome to the third statistics lecture. Last lecture we went through the visualization of data and the different methods to do that, such as scatter plots, box plots, and histograms. We also went through normal distribution and skewness, and then we end off with an example of descriptive statistics in practice. In this lecture, I will go through hypothesis testing as well as an example of how it can be used in the practice. So here we'll start off with hypothesis testing. For hypothesis testing, there exists a lot of different statistical tests they can use to test your data. And all of this, it depends on what kind of data do you have and what you want to find out. In this course, we will learn about the chi-square test and t-test, which are both parametric tests, which assumes that our data is normally distributed and that we have equal variance. So what does it mean that we want to do hypothesis testing? Basically, as you can see with the small smiley or wondering smiley down there, is it that you want to compare two hypotheses, a null hypothesis and an alternative hypothesis. So examples of these could be if you want to test if tooth flossing affects the number of cavities, then a null hypothesis could be that tooth flossing has no effect on the number of cavities, and then the alternative would be that there is an effect. Or you can have that you want to investigate if the amount of text highlighted in the textbook affects the exam scores. Then the null hypothesis would be that the text highlighted or the amount of text highlighted in the textbook have no effect on the exam scores. And alternative would then be that there is an effect. Another important term that we'll be using is degrees of freedom, which is the number of independent pieces of information that goes into the calculation of the estimate. And usually this is calculated by having the total number of samples and then subtracting one. So for example, if we're investigating 4 people, then they would have 3 degrees of freedom because there will be 4 minus 1. And finally, the chi-square test, as you can see on the top right, I've tried to make or find 3 boxes. So for the chi-square test, that's usually used for comparison of categorical variables. The t-test is usually for comparison of categorical and or continuous variables. And then finally, we have correlation, which I'll go over in the 4th lecture. So here we have a general overview of hypothesis testing. This box is from the Medical Statistics at a Glance book, and here it's split into 5 different stages of when you have to calculate or carry out the hypothesis test. So we always start with defining the null and alternative hypotheses on the study or for the study. Then we want to collect the relevant data from a sample of individuals. And then the third part, we want to calculate the value of the test statistics specific to the null hypotheses. So this could be, for example, if we're doing a t-test, it will be a t-statistics and so on. And then for the 4th part, we want to compare the value of the test statistics to value from a known probability distribution. So this could be a normal distribution and then the values for that specific normal distribution. In t-test is usually a t-distribution. And then finally, we want to interpret the p-value, which you get from number 4, where you compare the test statistics with the known probability distribution. And then from that, we get a result. So to start off, we have t-test. T-test is the hypothesis test that we want to use when we're dealing with numerical data and to some degree categorical data. And for if it's categorical, then we usually want to make it into proportions. And for t-test, we can split that into different types. So we have a one sample t-test, we have paired t-test, and we have unpaired t-test. So at the top right, you can see a figure with the 3 different ones. So for the one sample t-test, we want to see if there's a difference between a group and the population. And for the unpaired sample t-test, we want to see if there's difference between 2 different groups. And then for the final one, for the paired sample t-test, we want to see if there is a difference in a group between 2 points in time. So it's the same patient that you measure twice. start off, we have the one sample t-test. So this is the t-test where we want to see, or we want to find out if there's a difference between our group of patients and the population. And it is usually, or it is a test for numerical data. We have a sample from a single group of individuals and one numerical or ordinal variable of interest. So for example, this could be that if we want to test if our group of patients have the same triglyceride level in the blood as healthy individuals, and that we know that those healthy individuals have a mean of 1.74 millimole per liter, then we can use the one sample t-test. Another example could be if we wanted to find out if our sample of babies, for example, have the same weight as the population average of babies. Then we could also use one sample test or t-test. And for calculating the t-statistics or test statistics for the one sample t-test, we have this wonderful formula. So we start with the mean, the sample mean, and we subtract that from the mean of the population, which is something that we know. And then we divide that with the standard deviation, and that is also divided by the square root of the sample size. And from that we get the test statistics, which we then can compare to the known distributions. So for t-test specifically, that will be the t distribution that we compared to, and that is also one that you can find in the medical statistics at a glance book. So in table A2, there's a t distribution table where they have in the first column they have degrees of freedom. So that's the amount of sample, or the sample size, minus 1. And then following that, we have columns of different p-values with the different values underneath the p-value. That is the t-test, test statistics. So basically, you take your test statistics that you calculated and then compare it to the same amount of degrees of freedom, and then you see what p-value you would get from that. And then after that, you compare it to the p-value that you have specified. So usually we have a p-value of 0.05. So if it is less than 0.05, then typically that would mean that it's statistically significant, and then you should be able to reject the null hypothesis. And now we go to the paired t-test, which is a test between two related groups. So here you typically want to see if there's a difference between a group and then at two different time points. So for example, it could be that you have a patient, and then that patient, before he takes the drug, he gets some kind of measurement, and then after a while he gets another measurement, so after he takes the drug. And so that is what we typically mean with two related groups, which is something that we use for the paired t-test. And as an example, as I also said before, it can be the group could be a clinical trial, or it could be a clinical trial where a patient has a blood measurement taken before and after exposure to the treatment to see if there's a difference in the blood measurement. And again, this is also the t-test, so the way that you get results from this is very similar to the one sample one. So we have to calculate the test statistics again. The formula is a little bit different, but it is also very similar. So here, instead of subtracting different means, then we have a mean difference at the top part, and that is the mean difference between the group at two different time points. And then below we still have the standard deviation and the square root of the sample size. Same as before, the test statistics that we calculate, that is compared to a known distribution. Again, because this is a t-test, we compare to the t-distribution, and we still have the degrees of freedom in the first column and then the p-values after the following columns. And then this p-value that we find is what we base our statistically significance on. For the third of the t-test that we have, so we have the unpaired t-test here. So this is a test between two unrelated groups. So we typically here want to see if there's a difference between group A and group B. And in this case, we have samples from two unrelated independent groups. And we'll have to use the unpaired t-test then. An example of this could then be that we want to do a clinical trial where we want to see if we have to see if the treatment in two different groups are working. So we will have one group with exposure to the treatment, and we have another group where they don't have exposure to treatment, and then we can see if there's a difference between those two groups. Another example could be that you want to see if there's a difference in health between people with and without a university degree. Or another example could be that you want to see if two different machines produce the same weight of tablets, and then you would also compare those two, for example. So different from the other two t-tests, in the unpaired t-test we have to calculate a pool standard deviation because now we have two different groups that we're comparing. And this is calculated by the formula that I have on the right side, which is the S equals to the square root of the first sample size minus 1 times the standard deviation to the power of 2, and then we add that to the other sample that we have, or the other group, and then we divide everything with the number of freedoms or degrees of freedoms, which is the sample size of the first sample size plus the second sample size minus 2. And the minus 2 is because we have two different sample sizes. Usually when we only have one group, we just subtract 1. And then similarly to the other two tests, or the other two t-tests that we have done, we also need to calculate the test statistics. And the formula for this is very similar. Here we just use the pool standard deviation instead. Otherwise everything is the same. Again, you will compare that to the t-distribution because this is a t-test, and then you would see what the p-value for the test that you just performed is, and then you would make or interpret that. And now we move to chi-square test. So when we have two proportions with categorical data, we can use the chi-square test to find out if the proportions are the same in both groups. So that was for if it's two groups that are independent. If we have two related groups, we will use another test called McNemar's test. So an example of variables they could use for that, or independent groups, could be if you compared if you were married or married or not with the degree that you have gotten. Or it could also be if you were American or Canadian and compared with if you're right-handed and left-handed, you could also have that. For chi-square test, we often create a contingency table, which are tables with frequencies, and they show the observed values. So in the table 24.1, that is a table with observed frequencies, or an example of how what things that should contain in it. So if we have characteristics present and absent, and then we have group 1 and 2, then you would sum up in the A field the group 1 with present characteristics, and then the C field would be group 1 with absent, and likewise group 2 would have group 2 with present and group 2 with absent. And then underneath that, and on the right side, you would then have the total of the column or row. So in the column with the group 1 in total, that will be N1. So that would be where you sum up A and C. And then for the row with present, there will be this sum of A and B. And then additionally, you can also calculate the proportion with the characteristics. So there will be the proportion 1, as you can see in the table, would be A divided by N, which is the total for that column. So that is the overall proportion. So if the proportions in both groups are the same, we can expect that the overall proportion will also be similar to those, and we can therefore calculate an expected proportion. And this can be done by having the overall proportion that we also calculated in the table, as you can see, which is the P, and then using that to calculate the expected patients. So here it will be, we have the number of patients in group 1, so that is N, or N1, which is also the sum of the people with present and absent characteristics. And then we multiply that with the proportion that we have to see or to get the number of patients that we would expect. And the same we will also do for the group 2. So we have so we calculate the expected number of patients for both present and absent characteristics. For chi-square test, to then go from the calculated observed and expected values to getting the actual chi-square value, we want to have the 4 cells in the contingency table, both, so 4 cells from the observed and 4 cells from the expected. We would then, as you can see in the formula at the top right, we would have the sum of all the differences between observed and expected, and then minus that with a half to the power of 2, and then we divide that with the expected values. And we do that for each of the 4 cells in the contingency table. When we have then obtained the chi-square value, so the thing that we just calculated with the formula, we then compare that to the known probability distribution. So we calculate the test, we compare the test statistics. So the test statistics is what we call the value from all of these tests. We compare that with a known distribution, which in this case, because it's a chi-square test, we compare it to a chi-square distribution. And because we have written it as a contingency table, we have 1 degree of freedom here. And yeah, so you basically find the 1 degree of freedom and then find out which test statistics that you have calculated, and then find the p-value in the table. So now we have gone through some of the simpler tests in hypothesis testing, so the t-test and the chi-square test, which is something that is often used for parametric assumptions, or when we assume parametric with normal distribution and equal variance. But I did mention a lot of p-values in the different tests. So the p-value is the probability of obtaining our results or something more extreme if the null hypothesis is true. So basically what this means is that the p-value, or also called probability value, it is how likely it is for your data to occur under the null hypothesis. And this is all done by calculating the likelihood of the test statistics. So the test statistics is the one that we calculate in all the different tests. So the likelihood of that by a statistical test using our data. So for the p-value, it gets smaller as the test statistics calculated from our data gets further away from the range of the test statistics predicted by the null hypothesis. So as the p-value, it is a proportion, then that means that if we have a p-value of 0.05, that means that 5% of the time you would see a test statistics at least as extreme as the one that we have found in if our null hypothesis was true. So for example, if we have 2 groups of patients that each take a different medication, and we want to compare if those 2 medications is equally good, if we then calculate our test, our hypothesis testing, and we get a resulting p-value close to 1, then that would mean that the 2 drugs are probably, there's probably no difference between the 2 drugs. And then likewise, if we then move further away from 1, so usually we use 0.05 and below that. If that is the case, then we say that there's a statistical significance and there is a difference between the two. And that is also what I read here, that the smaller the p-value gets, the greater the evidence against the null hypothesis is. And by convention, or what we have done throughout time, typically we have considered the value less than 0.05 or 5% as significant and sufficient evidence to reject the null hypothesis. This also means that on 5% of the times that we do our hypothesis testing, we incorrectly reject the null hypothesis. So depending on how precise you want it to be, you can have this number higher or lower. But typically with this, if you have a lower value, then you would also need more patients tested to see the difference. So between p-values and confidence intervals, confidence intervals and p-values, they are similarly, or not similarly, but they are kind of linked because they're calculated from the same equations. So confidence intervals, they're calculated from same equations that generates the p-values. With hypothesis testing, we usually try to find an exact p-value. And with confidence intervals, we usually try to find the effects of interest, and that is then quantified, and we get a range of possible values. So this is also something that you maybe can see in the figure or graph. So if it is less than 1, or if it doesn't include 1, it's rather that, if it doesn't include 1, then we can reject, or we call it significant, which is also the p-value below 0.05. And then if it includes 1 for the risk ratio, so this is the ratio between two different groups. If it includes 1, then we say that we can't reject the null hypothesis, and there's no significance. So there's no difference between groups. So with this, it also means that by calculating confidence intervals for the measures of association between the two groups, we can also use that to address if it's statistically significant or not, even if the p-value is not calculated. So usually when we do give the confidence intervals, we give it with 95% confidence interval, which means that the interval is the values or the values that are outside the 95% confidence interval. Those are the ones that are unlikely to be true values. And for the confidence interval, to calculate them for the different hypothesis tests that we have learned about, we also have some simple formulas. So for the chi-square test, we compared it to, so that is why we compare proportions. So here we use the proportions to calculate the confidence intervals, plus and minus. So that's plus and minus the mean usually. 1.96 is then the optimal value for the that is for the 5%. For the unpaired t-test, here we have two groups and we have two values or two means. So you would take the difference between those, you would have the plus and the minus of the t-value for the 0.05 p-value. And then you would multiply that with the standard deviation of, and then times the difference between the two groups. And then finally for the one sample t-test, we would have the mean plus minus the t-value for the 0.05. And then you would multiply that with the standard deviation over the square root of the sample size. And we should then see something similar to the p-values that we also calculated or found. And then we can also reject or accept the hypothesis based on that. They should be similar. Now we'll go to type 1 and type 2 errors. So a type 1 error is where, or this is also known as the false positive. So this is the probability alpha. And here we, It's known as a false positive, and it occurs when we incorrectly reject a true null hypothesis. So that means that we will report our findings as significant when in fact that is not significant, and it maybe is something that occurred by chance. So as I said, this is the alpha value. So as you can see, probability alpha, which is the p-value below where we reject the null hypothesis. So this was the 0.05 that we have been using, or is the convention that we're to use. So we accept that there's a 5% chance that we get it wrong when I reject the null hypothesis. And again, we can also put this alpha lower. So for example, 1% chance of committing the type 1 error. But this lower value would then also mean that it's less likely to detect a true difference if there really exists one, and we'll probably need more patience. We also have the type 2 errors. So these are the false negatives. So they occur when we fail to reject the null hypothesis when it is really false. So basically we'll conclude that there's not a significant effect when there actually is a significant effect. And the probability for this one is then called beta, and that is also related to the power, which we will go through in the next lecture. But basically you can decrease the risk of committing a type 2 error by ensuring that the test has enough power. So this is something we'll learn how to calculate in the next lecture. But we can ensure that we have enough power by having a bigger sample size, or a large enough sample size. So why is the type 1 and type 2 errors important? It's basically we want to avoid the consequences of making these kinds of error, because that means that we are making some unnecessarily interventions and also wasting time and resources on that, because making a lot of the clinical trials, they cost a ton of money to make, and if we basically don't have enough power, or if we make these kind of errors, then everything is kind of wasted. And here I have two examples of type 1 and type 2 errors. So for the type 1 error, it would be if you're telling an elderly man, hey, you're pregnant. And here we know men can't really get pregnant, so this one would be falsely telling you're pregnant when you're actually not. And then for the type 2 errors, if you then have a woman and you're saying, hey, you're not pregnant when you're actually pregnant, then that will be the type 2 error. So here I have tried to sketch it out using the same table as before. So, and this is also using the same example with the pregnant man and not pregnant woman. And we'll have the type 1 error, which was the pregnant man, and would have the type 2 error, which was the not pregnant woman. And then you have the two correct decisions, which was pregnant and not pregnant. So here, just again to summarize, we have the general overview of the hypothesis testing. We have 5 different stages that we carry out our hypothesis test. We first define the null and alternative hypothesis for the study. So that could be pregnant, not pregnant, or difference or not difference in the treatment or something else. You will then collect the relevant data from the sample of individuals, and we'll also go through to how we calculate the number of individuals that we need in the power analysis part in the next lecture. Then the third part, or the third stage, is that we calculate the value for test statistics specific to the null hypothesis. And here we would use one of our tests. It could be the t-test for the unpaired, paired, one sample. It would also be a chi-square test or another one that you might learn in the future. We will then compare that value of the test statistics to values that we know from the known probability distributions. So that could be, for example, t-distribution or chi-square distribution. or something else for different tests. And then we will interpret the p-values for those and then find out if it's significant or not. And then typically we would also calculate confidence intervals, which is also something that you usually have to report in studies now. So yes, I hope this general overview is good. So now we will move over to the example. This example will be a continuation of the previous one from the other lecture. So last time we want to see if our sample, or what the weight or mean weight, and how much the standard deviation of that sample was. That was the last lecture. This time we want to see if we can get closer to the expected weight by changing some of the settings in the tablet pressing machine. And here again, we measure the tablets in the same way as before. So we use the same general overview that I also showed before. So we first want to define null and alternative hypothesis under the study. So we know that we have two groups. So the tablets that we made first and weight, and then change the machine or change some settings in the machine. So we have a new group now, and weigh those. So they're not those are independent of each other, so it's unpaired t-test. So two different groups. We start with the first step, as I said. We define the null hypothesis. So we are saying that the null hypothesis is that there is no difference between the two groups. So the difference is equal to 0. And then we have the alternative hypothesis, which is that there is a difference between the two groups, which is it's not equal to 0. Then we go to the second stage. So here we want to collect the relevant data for the samples of individuals. So we make the new tablets and we measure those weights. So we have the first tablets, so that was from the first lecture, or the first batch of tablets that were made. Then we have the second tablets, which is from new batch. Then we go to the third stage, where we want to calculate the value of the test statistics. So first off, we have on the right side, we have the tablets. We have the weights of all the tablets. And then we figure out how many measurements do we have. So we have 18 in each group. Then we want to find the mean weight. We find the variance for the different groups, and we find the standard deviation for those two groups. Then we want to calculate the pooled standard deviation, because now we have unpaired t-test. So we have two different groups. So on the left side, I have the formula from the book, and then on the middle, I have tried to calculate it. So we have n minus 1. So that's the number of measurements or number of tablets minus 1. So we have 18 in both groups. So that means that will be 17. We multiply that with the standard deviation for the first group, which is 21. And then we have that to the power of 2. We add that to the second group. So again, we also do the 17, and then this time we multiply with 18 to the power of 2. And then we divide that with the number of samples for both, so 18 plus 18, and then we subtract 2. And then to all of that, we take the square root. And from that, we get a pooled standard deviation of 19.6 milligrams, because all of these weighings are in milligrams. Then we want to calculate the test statistics. So first, we have the means. We subtract those two from each other. So 700 minus 729. And then we divide that with the pooled standard deviation that we just calculated, and multiply that with the square root of 1 over 18 plus 1 over 18. So that's the number of tablets in both groups. And then we get a test statistics out of that. So here we get one which is negative, but that doesn't really matter because it's fairly the same. So you can just remove the minus sign. So you will get the same p-value from that. Now we go to the next step, which is comparing the test statistics value that we just found out to the known probability and interpret that p-value. So here I have found a bigger table, so you can find these on the internet very easily by just searching for the t distributions. But it's also in the book. The book just have fewer p-values because it doesn't have enough space to show everything. But basically, we'll look at the t-distribution because we now did a t-test, and we see that there is a statistical significance. So there is a difference between the two means using our test statistic that we just calculated. And how do we know that? We go to the table, we find the number of degrees of freedom, which is 34 here. So we have the 18 plus 18 minus 2. So we find 34, and then we look at what p-value we get using our test statistics. So here we can see that our p-value for a two-tailed one, so we have both, so it can both be, the difference can both be higher and lower, and not just one way. We can see that our t-value or test statistics is 4.4, and here the highest one we can see is 3.6, and even like over there we have a p-value of 0.001, and because our number is higher, the p-value is even lower than that. And by then looking at that number, we can see that it's statistically significant if we're using the 0.05 p-value. So this was the lecture for this time. It was on hypothesis testing, and I hope it was useful and understandable. And if not, please just send me an email, or we can discuss it during the seminars. In the next lecture that we'll have, we'll cover calculation of the size, so the sample size, the power calculation that we also very briefly touched upon today, and then finally correlations. So look forward to the next one.